So this is the first recorded lecture for Math 140 Business because there were technical difficulties, i.e. I forgot to hit record last time. If you want to watch a video on the first two lectures, my Math 140 Science, SCI videos cover exactly the same material so that you can watch them and catch up on anything regarding those first two videos. So we're starting here quickly before we move on by answering a couple of homework questions. So this is question number 7, El Nino and the monsoon. It says the Earth is interconnected. For example, it appears that El Nino, the periodic warming of the Pacific Ocean west of South America, affects the monsoon rains that are essential for agriculture in India, which is pretty cool. Here are the monsoon rains in millimeters for the 23 strong El Nino years between 1871 and 2004. So it gives you a data set, correct? Right, it gives you a bunch of data. And it says, make a stem plot, or at least figure out which of these is the correct stem plot. So I'm gonna share my screen for a second. Okay, so it says to make a stem plot of these rainfall amounts, round the data to the nearest 10. So 628 would round to what?
6.3.
Not 6.3, 630, 630.
Oh, yeah, yeah.
Right? And we want the stems to be hundreds, and we want the leaves to be tens. So for example, 6.3 would be 630, correct?
Yes.
Yeah.
6.5 will be 650.
Mm-hmm.
Now, would any of these be 650? Let's see, 651 is 650, and 653 is 650. So those are good, and 628 is 630, and then 670, anything around the six, oh, someone's chatting, what are they saying? Yeah, just chapter 1. So I don't see any that would round to 670, unless, oh no, 669 will go to 670. Okay, so we have these options. So what's wrong with these? So let's take a look. This is a split stem, and this here is a non-split stem. 6, 6, 7, 7, 8, 8. Oh, well, look at that. Here's a mistake already. You see it? Where's the first half of the 9 stem? Hello, you there?
Oh, yeah, yeah.
This can't be right. It's missing the first half of the 9 stem.
Yeah.
And this one can't be right because there's no 100. That's nonsense.
Yeah.
And this one.
This is 6.4, so it just only mentions about 6.4, so it's not true.
Wait, this one here?
Yeah.
Oh, yeah, because it should be 630.
Yeah, yeah. So that's not right.
So it's got to be stem plot 4, and it is stem plot 4.
Yeah, I got stem plot 4.
Okay. So the stem plot with split stems does not display the shape of the distribution, true or false? Well,
it was false.
Well, yeah, because it kind of, that's the whole point of it, right?
Yeah.
I mean, the whole point is that it does. And how would you best describe the shape? It looks like a little right skewed, right? We got a little tail here on the right.
Oh, okay.
Right?
Yeah.
It looks like symmetric with a little tail on the right. So I would say it's slightly skewed to the right. Yeah, somewhat skewed to the right. Find the value of the median. Well, how many data points are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 18, 21, 22, 23 data points, which means which one is going to be the one in the middle?
12.
The 12th, the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 7, 8. This one here, 7, 8, which is of course 780, would be the median, right? But they want the actual value of the median back with the original data, not with a stem plot. So which one rounded to 780? This one here, 784, the second one.
Okay.
Does that make sense?
Yeah, it does.
All right, and then someone asked number 8, right? Did I remember that?
Actually, can you please?
Oh, you skipped step 5.
What?
Oh, you skipped step 5.
Oh, there was more? I'm sorry, 1 second. There was more. What is the spread of the distribution? So
Is it from the beginning to the end?
Low to
Oh,
high,
like-
right?
The low to high, yeah.
Low to high, 604 to 957. 604 is the smallest, 957 is the biggest, low to high.
So just those two?
Well, that's no, I mean, the answer is 604 to 957, low to high.
Oh, okay.
You got to list it.
Yeah, okay, got it.
Okay, so I'm sorry, someone was asking something a second ago. What was that?
I asked if you could please do number 6 instead of 8.
6 instead of 8. So carbon dioxide emissions?
Yeah, I was really confused on that because I thought my answers were correct, but they ended up being wrong.
Let's take a look. So burning fuels in power plants or motor vehicle. Okay, the below displays 2007 CO2 emissions per person from countries with populations of at least 30 million in that year. Okay, we got all this stuff. Why do you think we choose to measure emissions per person rather than total carbon CO2 emissions for each country? Obviously, countries with a greater population are going to have a greater amount, right? I mean, it's not fair to compare, United States to Vatican City or something like that. But if you normalize by looking at it per person, you can get a much better feeling for how much each person, metric tons per person, right? That's what we have here, is producing. Does that make sense? That seems reasonable, correct?
Yeah, that part was.
Okay, so next step 2, make a stem plot of the data, use whole tons per person and tenths for the leaves. So for example, the first one will be 0.0, whole and tenths, 4.1, 4.7, and so on, correct?
Yes.
Okay, so we have all these different stem plots. The first one should be 0.0. So the first two look wrong. 3 and 4 might be correct because they both have 0, 0. Did you have any questions on this part?
Yeah, that's the part that like kind of confused me because none of the numbers really added up to the actual. I put stem plot 3, but I don't know, just none of the numbers really added up correctly whenever I like counted it and then I counted the ones.
Well, what do you mean it added up correctly?
Like I don't know how to, like none of them corresponded to the graph like perfectly. I understood like the rounding and stuff like that.
Okay, well, let's take a look. According to this, let's look for a difference. A big difference between them are these zeros here, right?
Yeah, that's why I omitted the 4th graph. 'cause-
Okay, so yes. Okay, so according to this, there should be a 12.0 through a 15.0.
Yeah.
I don't see anything that would indicate a 12.0 to a 15.0.
Yeah.
But the rest of them, 0.0, 4.1, here's 0.0, here's, okay, well, that's weird.
Yeah, and then whenever I got to the other one where it was like asking me to count to the 20th digit, I'm pretty sure it was this question.
Yeah,
It
okay.
like wasn't the middle one. There was like I believe 40 something and the 20th wasn't the middle one. That's why I was confused. Like
Yeah, no, that's fine. You're gonna find a lot of mistakes in this program, which is why I don't like using it. But they say stem plot 1, and right off the bat, this one here, 0.0, is not located in stem plot 1.
yeah.
So yeah, so this is one of those that just bad answers. And because of that, how do you describe the shape of the distribution? Well, if stem plot 1 is correct, it's certainly skewed to the right. Right? Because it comes up, here's the peak, and it tails way off on the right side.
Yeah.
Right? So slightly uneven and skewed to the right, but it's not really slightly uneven. I mean, it's very uneven.
Yeah.
All right, so let me pass along question 1.36 to the powers that be. Okay. Yeah, you'll find some of those like that. You'll just find wrong answers, huh?
All right, Professor. Could you go through question to the final step for that question, please?
The
Onto
same
steps.
one.
Yeah. for numbers.
So then the final one says, by counting your entries in the stem plot, what is the value at the center? There are 39 countries, so it's going to be the 20th one. If stem plot 1 is correct, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 35. would be the 20th one. Or 3.5, whatever it's measuring, 3.5. So that seems to be correct. And then ignoring the outliers, what is the spread of the distribution? Well, the outliers are most likely in these two here, which are way out. So according to this one, it'll be 0.1 to 11.0. So it says 0 to 10.8, which again does not correspond at all to the distributions. That's just nonsense.
Yeah, I also don't see 15.3 on the table either, because this one has a 15.3 in the thing, but there's
Yeah. So this is not, this is nonsense. This is just nonsense. And then which countries are outliers? Well, assuming that these ones here, I mean, it's not even on the sheets. I mean, United States for sure, and maybe Canada. So maybe United States and Canada are the only one. Enter the number that corresponds. United States is 1, Canada 1. Yeah, only United States and Canada will be outliers. Nothing else is really, just by looking at the data, nothing else is really far enough away.
Okay, got it.
All right, because you have 10.8, 10.5, but that's pretty close. You have some 9s, you have some 7s, you have some 6s, 8s, but 18.9, 16.9, those are way off base. But you can just tell that this problem doesn't make any. I mean, the answers don't correspond with the data.
Yeah. So yeah, that was kind of confusing too.
Yeah, 100%, 100%. These questions were not picked by me. These questions are picked by my boss. He gave me a list of which questions to ask. This one is certainly a bad one. I will pass along to the appropriate people, and I will give them a stern talking to.
Okay.
Okay. Meanwhile, so that's it for just going over a little bit. Let's now jump ahead to continue in chapter 2. So last time we had started chapter 2, and so this is a quick recap. We had measures of center. Measures of center. Can someone remind me, please, what were the two measures of center that we did last time?
Median and mean.
So we did the median and we did the mean. The median and the mean were our two measures of center. And we also talked about the concept of a resistant measure and a non-resistant measure. Can someone remind me which of these is a resistant measure and which of these is a non-resistant measure?
Mean is non-resistant and the median is resistant.
Good. The mean is non-resistant, which means it gets pulled by outliers. The median is resistant, which means it resists the pull. It can't necessarily eliminate it. I'm not suggesting the median can't change, but it's harder to change. So let's compare the three shapes that we're dealing with. Shape number 1 is symmetric. And if a symmetric graph, a basic symmetric graph might look something like this. Okay, it's the famous bell curve.
Professor, you're not screen sharing.
You're right, I'm not. Thank you. I'm gonna add that right now. 1 second, I apologize. At least I'm recording, so hey, so much for, one baby steps, right? So share content, only the host can share content. I gotta add that. Okay, so here we go. Okay. All right, so as I was saying, so we have a recap, measures of center. We have the median versus the mean. The median is a resistant measure. The mean is a non-resistant measure. And if we have a symmetric looking graph, where is the mean and where is the median located for a symmetric graph? Remember, the mean is the balance point if you physically build it and you want to balance it on your finger. And the median is the midpoint of your data. So for a symmetric graph, where is the mean located and where is the median located?
Aren't they both in the middle?
They're both directly in the middle. And if it's only approximately symmetric, they're both approximately in the middle. But they're both, if it's a bell curve, like we're going to cover in chapter 3, then they both be exactly in the center. The next question is, what if it's right skewed? what if my graph, my data, my distribution looks more like this, where we got a nice long tail on one side. So if you look at it from the balance point perspective, instead of the balance point being at the peak like it was before, which way would the balance point shift? Would it shift to the left? Would it stay in the middle? Or would it shift to the right? If you were to balance this on your finger, where would the balance point shift?
To the left?
So if I had the original data like this, if that was my original symmetric graph, where the balance point was directly in the center, and then I add extra data to the right, i.e. I add extra, if I'm actually constructing this physically, if I add extra material on the right, you're going to say the balance point is going to go to the left?
Of course not, because it'll be going to the right.
And okay, that's what I thought you said. So yes, the balance point, the mean would shift to the right, but the midpoint would also shift to the right a little bit because I have more data on the right side than on the left. So how do we incorporate the non-resistant and resistant natures of the mean and the median? It's the fact that the median will shift a little bit to the right, but the mean will shift more. So on a right skewed graph, the mean shifts more to the right than the median does. Means are pulled more in the direction of skewness than medians are. And if it was a left skewed graph, then what would be the relation here for a left skewed graph? Where would the mean and median go in the case of a left skewed graph?
Shift slightly to the left.
Which one shifts more?
Mean.
Mean.
The mean would always, well, I use the word always with quotation marks because you can actually create very weird scenarios where it's not true. But for our class, the mean will always shift more than the median. Okay. And that is another manifestation of this concept of resistant versus non-resistant. Does that make sense?
Yes.
Yes.
Okay. So that's all about measuring center. But measuring center is not enough. We also want to measure spread or variability. I can draw two distributions that have the same center, right? Think of the following distribution versus, that's bad. The first, okay, let me do this again. So that one is good versus something like that. In both cases, if I asked you for the balance point, if I asked you for the point where you can balance it on your finger, in both cases, the mean would be directly in the center because they're both symmetric graphs. But in the first case, most of the data is very close to the mean. In the second case, most of the data is very far from the mean. So that even though they have the same center, the second one intuitively has a greater variability than the first. And we want to have a measure of the variability of our data. So how do we measure variability? Anyone know the two standard approaches for variability that we're going to use? You probably only know this if you've taken some stats before in your life, but anyone know offhand which measures of variability we use? So when using the mean, always use the standard deviation, shortened as STDEV, as your measure of variability. When using the median, always use the, anyone know? Going once? Going twice? All right, it is the interquartile range. Interquartile range, often denoted the IQR, as your measure of variability. Has anyone here ever heard of either the standard deviation or the IQR?
I've heard of standard deviation, but I forgot what it is.
No problem. Good. So we can do it from scratch. I'm looking for a good example to use to illustrate. So first, let's examine the IQR. It is the easier one mathematically. So first, let's examine the IQR, and we will do so via the following example. So consider data points 5, 10, 10, 10, 10, 12, 15, 20, 20, 25, 30, 30, 40, 40, and 60. Okay, so you have some data that you're taking, and we're going to find the IQR. So first, some obvious values. What is the minimum of the data collection? What's the minimum value?
5.
5, that's a no-brainer. What is the maximum of the data collection?
60.
60. So what would the spread be in terms of the definition we gave last time for the spread?
5 to 60.
5 to 60. The range, on the other hand, is a number. The range is max minus min. So what is the range equal to for this example?
55.
55. The problem with the range is that one outlier can make the range be huge when it might not be representative of all your actual data. Correct? So we want a value of spread, a value of measure of variability, which eliminates bad data points, or at least a few bad data points. So here's how we find it. Step 1, find the median. Now, we learned how to do this last time. If we have, first of all, how many data points do we have? An odd number or an even number?
We have 15.
So we have 15. That's an odd number, which means which one is the median?
Number 8.
The eighth data point, which is which one?
20.
20, but it's 20, but it's important. This is important. Which 20 is it? The first 20 or the second 20?
First.
First. So this one here, which I'm going to label as Q2, another term for the median. Find the median equals Q2 equals 20. So step 1 is to find Q2, the median. Step 2. Find the median of the left half of your data, which we're going to call Q1. So if I look to the left of 20, I don't include the median itself. I never include the median. If I look to the left of 20, how many data points are there?
7.
Which one of those is the median?
The third 10.
The third 10. So I'm going to call that Q1. So that equals 10. And then step 3, find the median. Can anyone guess this? Of the
Adjacent.
adjacent, what does that mean?
I'm kidding. Third. Or sorry, the right side.
The right side of the right half of your data, which we're going to call what?
Q3.
Q3. And what does that equal to in this case? Well, first of all, which one is it?
The second 30.
The second 30, that's Q3. Okay, those are just definitions. We all with me so far on which ones, how to find Q1 and how to find Q2 and Q3 and the max and all those stuff?
Yeah.
So step 4, the IQR is defined. Can anyone take a guess as to how the IQR is defined? It is the interquartile range. So think of how range is defined. And it's the interquartile range, where these Q's stand for quartile. The first quartile, the second quartile, the third quartile. So someone take a guess as to how the IQR is defined. It could be wrong. I don't even care. Just take a guess. The interquartile range.
Is it Q3 minus Q1?
Q3 minus Q1 it is, which in our case is 20. The fact that it's equal to the median is a pure coincidence. So this is how we find the IQR. You find the median, you find the left median, you find the right median, you subtract those, and that's the IQR. That's a definition. Does that make sense in terms of how to do it?
Yes.
Okay, but now we will use the IQR to find suspected outliers. How do you know if something is an outlier or not? Looking at this data, would you suspect that 5 is an outlier?
No.
No, it seems fairly close to the rest of the 10s. Would you suspect that 60 is an outlier?
Yes.
Yes.
Okay, well, let's see if it is or not, or at least let's see if we will consider it to be an outlier or not. Here's how we do it. Step 5, because you got to go through the first 4 steps. What is 1.5 times the IQR?
30.
30. Then we evaluate Q1 minus 1.5 times the IQR and Q3 plus 1.5 times the IQR. What is Q1 minus 1.5 IQRs?
Negative 20.
Negative 20. And what is Q3 plus 1.5 IQRs?
30, 50.
Q3 was 30.
Oh, wait, sorry.
60?
60.
60, correct? So 7. Any data points beyond these numbers is considered an outlier. So, do we have any data points beyond -20?
No.
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 Do we have any data points beyond 60?
No.
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 No. So by the 1.5 times the IQR rule, this collection of data points has no outliers. However, of course, 60 falls right in the border. So if I was really doing a true investigation of this that had actual repercussions on policy, I would probably want to do a little more deeper analysis. But at a very superficial math 140 level, there are no outliers for this data set. Does that make sense?
Yes.
Does this-
Professor,
Yeah,
can you explain again where you got the 1.5 from for the?
that's people
statistics?
a lot smarter than me figure that one out. That's not my call. That's
So it's just default, that's the one that always goes?
That's
Is
the
that
one
0.5?
that's the one statisticians use. They use the 1.5 times the IQR rule.
Okay.
But again, it's not like, and God said, let you multiply IQR by 1.5. This is some arbitrary number that was picked by statisticians, which means when it comes time to actually say if it's an outlier or not, the best we can say is that it is a suspected outlier if it's beyond it, and it's not a suspected outlier if it's not beyond it. Whether it truly is an outlier or not is a whole nother question. All we can come up with are suspected outliers. Does that make
Got
sense?
Yeah, I got it. Thank you.
Okay. And of course, if I had an even number of data points, the details of how to find the medians might be a little more complicated, but the 7 steps will be exactly the same. Does that make sense?
Yes.
Yes.
Okay, so let's do another example of, with this time with an even number, just to do it. And we will also go one step further and come up with a visual display for our collection. And I want to do one that has an outlier so I can demonstrate something. You know what? I had one in my other textbook. Give me a second. I had a good example here, so hold on. Okay, so we're going to do the following example. Okay, so here's an example. 10, 10, 10, 10, 12, 15, 15, 20, 20, 30, 35, 35, 40, 45, 50, 50, 55. The magic of the iPad makes them smaller. 60, 65, 100. All right. So how many data points do we have in this collection? How many? I'm sorry?
20?
20?
20. So with 20 data points, where is, of course, we know what the min and max are. Those are the obvious ones. But with 20 data points, where is the median located?
Between the 30 and the 35?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, right here.
10.5,
So what is the median equal
which
to?
is 32.5?
32.5 would be the median. We agree?
Yeah.
Okay. Now, let's find Q1, which is the median of the data points to the left of 32.5. How many data points are to the left of 32.5?
10.
10. So where's the median? Sorry, yeah, where's the median of the left?
12.5.
Yes, so Q1 is equal to 12.5. And what's Q3?
Will be 50.5.
It would not be 50.5.
52.5.
No, it won't be that either.
Would it be 45.5?
Won't be that either.
Would it just be 50?
Straight up 50.
Mm-hmm.
It's halfway between two 50s. So it's just 50. Do we agree?
Mm-hmm. Yeah.
Okay, so now that we have those, what is the IQR?
Sorry. Why is the middle between 12 and 15 12.5?
It should be 13.5. Thank you.
Yeah, thank you.
My bad. Thank you. Thank you.
Sorry, I can't do math. 13.5. All right, so what's the IQR?
It'll be Q3 minus Q1, and then it will give us like the answer.
I don't trust my math anymore.
37.5.
I have 36.5 because we changed 12.5 to 13.5.
Yeah, true.
I've done that, it would be 37.5. So what is 1.5 times the IQR? And by the way, that 100 at the end, make it 110. So it's an actual outlier. 100 in hindsight, 100 wasn't big enough. Doesn't change any of our calculations so far. It just makes sure that it's an outlier. So what is 1.5 times the IQR?
Is it 44.75?
I did not get that. I use my calculator, so I know.
Is it 54.75?
54.75. So now when I do Q1 minus 1.5 times the IQR, tell me why I don't need to spend time to actually calculate this. Why do I not need to spend time to actually calculate this? I mean, what I mean by that is to get an actual specific value.
You don't have to spend time because you know it's going to be negative and the lowest is a 10 anyways.
Excellent.
You know it's not going to be under.
Excellent. So without knowing exactly what it is, I know it's negative. And it's definitely going to be past 10. What is Q3 plus 1.5 times the IQR?
$104.75.
104.75. As a result, are there any outliers or suspected outliers?
Yes.
Which one or ones?
110.
So therefore 110 is a suspected outlier. Does that make sense?
Yes.
Everyone else? Everyone okay with that? Seems reasonable. Okay, so what we're going to do now is we're going to follow up with a third graphical display for quantitative data. Someone remind me, please, what are our first two graphical displays for quantitative data? I forgot. What do we have already?
Histogram and stem and leaf.
Histogram and stem and leaf plot. Although I think we also did a dot plot on the workbook, I think. But now We're gonna add another one. So now we're gonna introduce a box plot. Okay, a box plot. And it uses step 1, determine the 5-number summary of the data. Determine the 5-number summary of the data. What do you think, based upon what we just did a few minutes ago, what do you think is the 5-number summary of the data? What 5 numbers?
Q1, Q3, Q5, and then,
Wait, Q5, what's Q5?
sorry, Q3. I saw 1.5, I got distracted.
All right, I have Q1, I have Q3. What else?
Q2.
Can we use Q2?
Q2. What else?
IQR?
The IQR is not, because I can get that immediately from Q1 and Q3.
Mm.
So it's not, I don't need it as an additional.
Is it your,
Would it be
Your-
the maximum?
Yes, the maximum and the minimum. The 5-number summary are the minimum, Q1, Q2, Q3, and the maximum. And the way we create the box plot is as follows. We make a number line. In our case, we're going from 10 to 110. So here's 10, 20, 30, 40, 50, 60, 70, 80, 90, 100, 110. So what we do is as follows. We're going to put a dot at the minimum, a dot at the maximum, vertical lines at Q1, Q2, and Q3. And that's going to create a box. And that's our box plot. Notice the 5 numbers, the edges of the different sections. Now tell me, roughly, how much data falls in this area here, and how much data falls in this area here? Roughly what percent is to the right of Q2, and what percent is to the left of Q2?
%25%?
To the right or to the left? Which side?
The right?
Both
And how
sides?
much- so 25 to the right, and how much to the left? 75?
Yeah.
So why would it be 75% on this side and 20, I'm just curious, and 25% on that side?
To really be based like on the numbers like that were given to us, like from like the 10 to 110. And then
Well,
like 10, it goes from like 10 to 65. So it'll pretty much go on like the left side.
wait, 10 to 65, I think that was the previous data points, wasn't it? No, what's 10 to, why is 10 to 65? What happened to the 110? You know,
So it's from 10 to 110, but like on the left side, it like our box is from like 10 to like 50. So
yeah,
there's more 10 to 50 than there is 60 to 110.
okay,
Yeah, so that's why like that's why I was thinking about it like on the left side it'll be like a higher percentage
okay.
than
Well-
compared to the right side.
Well, let me see this question. As a general rule, Q2 is which point amongst the data? When you write your data points from lowest to highest, where's Q2 located?
It'll be located at 32.5.
Well, in this example, yes, but I'm saying in general, in terms of the percentage of the way through the data, 10% of the way through, 20%, 30%, 40%, Where
Half
is
of it.
half, right?
Yes.
So doesn't that mean that 50% should be roughly on that side of Q2 and the other 50% should be on that side?
Yeah, but that happens because like
Yeah.
there are like multiple like same numbers, right? Like there are 4 tens.
Doesn't matter. Doesn't matter. In general, Q2 divides the data into the left half and the right half. And when I take Q1, isn't that the median of the left half?
Yes.
So shouldn't that divide the left half into half and half itself?
Yes.
That tells me that there's approximately 25% of the data in each of these 4 sections. Between the minimum and Q1 is roughly 25%. By the way, that's why it's called the first quartile, because it takes the first quarter of the data. Between Q1 and Q2 is another 25%, the second quartile, the second quarter of the data. Q2 and Q3 is 25%, and then Q3, the maximum is 25%. Does that make sense? Does that seem reasonable?
It's reasonable, yeah.
Yeah.
Okay, now, based upon that, would you say that this data is symmetric, skewed to the left, or skewed to the right?
Skew to the right.
It is skewed to the right. If I had to graph this, it would probably look something like that. 25% in the first piece, 25%. Of course, I'm not the greatest artist, so I know these aren't perfect, but something like that. Maybe I can fix it a little bit. Something like that. So we can tell by the box plots, we can get an idea of whether it's symmetric or skewed based upon the size of the boxes and the whiskers that are coming out of the box. This used to be called a box and whisker plot. Box and whisker plot. They don't call them that anymore, but that's what we used to call them, the box and whisker plot. Just like we used to call it the stem and leaf plot, now it's just a stem plot. It used to be called a box and whisker plot. Does that make sense so far? Yes,
Yeah.
you so?
Yeah.
Okay, so now step 2 is make a modified box plot. The first step was about making a box plot. We find the 5-number summary. We plot it with this box configuration, and we call that the box plot. Now we're going to make what's called a modified box plot. And I'm going to do it. I'm going to make the change, and then you tell me what I did differently. That's my modified box plot. How does my modified box plot compare to my original box plot?
You didn't put in the outlier.
I did not include the outlier in my whisker. I stopped at the highest non-outlier, which in our case was 65. And then I just kind of threw in a little star at the outlier. That's the modified box plot.
And in most cases, like, do we always have to modify it, or do we just leave it as?
If they don't ask for a modified box plot in this course, I would not modify it.
Okay.
But out there in the world, if you're ever making a statistical analysis and you decide to use box plots, a modified box plot is preferable.
Got it.
Okay.
Perfect.
Okay. So any questions on how to create a box plot or a modified box plot? By the way, notice with the modified box plot and recognizing that 110 is a suspected outlier and therefore ignoring 110, what would the shape of the distribution be now?
I think it would still be skewed slightly to the right, but it's mostly like, it's like slightly skewed only, not.
I love it. Perfect. I would still say it's skewed to the right, but slightly is an amazing word to use. Okay, because you can see that, you know, over here versus over here, there's certainly more on the left, on the right side than the left, or at least not more, but it's spread out more, which gives you a little bit of skewness. So it still is to the right, but not nearly as much as it was before. Does that make sense? So any questions on the IQR, the 5-number summary, or box plots?
No.
Relatively straightforward?
Mhm.
Okay. So all of that, and this is important, all of that is to be used if you're using the median. Hopefully I said that somewhere in the beginning. Yes, when using the median, always use the IQR as your measure of variability. What about if you decide that the mean is the more appropriate measure to use? So what about when using the mean as your measure of center? So the answer we already said, we use the STDEV. We use the standard deviation. So we need a formula for the standard deviation. Unfortunately, it's a little more complicated than finding the IQR, although it has fewer steps. But here's how we do it. So given data x1, x2 through xn, step 1, find x bar. Someone remind me, what's x bar again?
The mean.
The mean, right? So the first thing we do is we find the mean. Okay. Okay. Then step 2, find the sample variance. S squared, which is equal to the following formula. So first, write that down before I will explain it. So what do we do? After you find the mean, you take each of your data points, x1, x2, x3, all the way through xn. You subtract the mean, square them all, add them all together, and then divide by n minus 1, which is 1 fewer than the number of data points. Finally, step 3, find the STDEV, S, which is nothing more than the square root of S squared. So let's do an example to illustrate this. And I'm going to do it in 3 ways. I'm going to do it by hand. I'm going to do it on my calculator. And then I will do it on an online calculator. So you can see but they all, of course, give the same answer, the correct answer. Okay, so the data is 5 points, a small data set. What is the first thing that I do here?
What do you
The
put
next
them like
part.
in order? Oh,
Sorry,
Find the mean.
find the mean. How do I find the mean?
Add them all divided by 5.
Add them all divided by 5. What do I get? What do you get? What do we all get?
$548.
548. So step 1, we find the mean, 548. Next, we're gonna make a table here because I want to demonstrate something on the table. And these are my 5 deviations from the mean. X1 minus X bar, X2 minus X bar, X3 minus X bar, X4 minus X bar, and finally X5 minus X bar. We have my 5 data points, so finding the deviation should not be tough. What's the first deviation?
It'll be 650 minus 548.
Correct, which is what?
102.
102. What's the second deviation?
It'll be 490 minus 548.
Which becomes what?
It'll be negative 58. I
Negative-
mean, 58. Yeah, 58.
Okay. I agree with all that except for the uncertainty halfway through, but I agree with your final answer. What's the third one?
It'll be 580 minus
32.
540. Yeah.
Which is 32. What's the fourth one?
Negative 98.
Negative 98. And what's the fifth one?
22.
22. And when you add them all together, not that we have to do this for this particular problem, but it's illustrative. When you add them all together, what do you get? And Dinara, I just saw your text, so you're only 2 minutes late. I'm going to put you here on time.
0.
Thank you.
You get 0. Deviations always add to 0, which means adding them and dividing by n minus 1 does nothing because we will always get 0. Why do we get 0? Because some of them are positive, some of them are negative, and we have cancellation. What are the standard simple 2 methods of getting rid of a negative number in math? I'll give you one, squaring it. If you square a number, if it's negative, the negative goes away, becomes positive. What's another method of getting rid of a negative?
Add it with the same number.
And what do we call that?
Absolute value?
What, sorry?
Absolute value?
Absolute value. Right? The absolute value of a number is getting rid of negatives, makes everything positive. So why is it that we square them before adding? Why not just do the absolute value before adding? The answer is you could, but mathematics of absolute values, especially when it comes to calculus, which is not a prerequisite for this course, but just in general, is much more complicated than mathematics without absolute values. And a lot of amazing properties and things that we can do with squaring, we could not do with absolute values. So essentially we make a choice and we do it this way because it makes other things easier. So what we're gonna do now is we're gonna square each of these deviations. We're gonna square each of these deviations. So we have D1 squared, D2 squared, and so on. What's the first one squared? Anyone?
10,404.
10,404. The next one?
3,364.
3,364. The next one?
1,024.
1,024. The next one?
9,604.
And finally, the last one.
484.
And now what we're gonna do, we're gonna add those up together because that's this step right here. At this point, we have the numerator now. We add them all up together. What do we get? 10,400. Sorry, that was from before. What do we get when we add them all together?
I got 24,880.
24,880. So now that we get that, now that we've added up them all and squared them and added them, the whole thing, what do we do next according to the formula?
Square.
No, not squared. We just calculated this numerator here, right? We just took all the deviations, squared them, and added them all together.
You
So what do
take
we
the
get?
square root of it.
Not yet.
You
Oh,
divide-
divided by 4.
Divided by 4. So 24,880 divided by 4. This is my S squared. And I get 6220. So the sample variance is 6220. And therefore, what is the sample standard deviation?
I got 78.8669.
Yeah, so 78.87 approximately. This would be the sample standard deviation for this particular problem. Okay, so what I'm gonna do now is I am going to show you how to get this on a TI-84. So TI-84, you'll see right here in the middle is a button labeled stat or statistics. So hit stat. Hit the wrong button. Hit stat. Okay. When you hit stat, you should have this pop up, edit, calculate, and tests. We are going to edit. So you want to hit enter. And what you'll do is you'll get a list. And you're going to put your data into the list. Mine's already in there. So for L1, you're going to input 490, 580, I can't read backwards, but is that 450, 420? I don't know. I can't. 450, 570, and 650, it looks like. You all with me so far? Yes? No, maybe so?
Yes, yes.
Yes.
Then hit stat again. But this time, we're no longer editing. This time, we're going to go to the right to calculate. And we're going to do the one variable stats because we only have one variable here. Only an X, nothing else. So one variable stats, enter, 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 calculate. And it gives us a bunch of data. Does one of them look familiar based upon what we just did?
7SX 78.866.
Right, so SX, the standard deviation of the X variable is 78.87, just like it was by hand. Of course, much faster with this, which you get to use on tests. So other calculators can do it too. I just don't know how to do it with other calculators. So know how to do it with this one.
Are we
Earlier,
also gonna be able to use it like on the final?
yes.
Okay.
Yes, you're welcome. Now, there's also a program which I'm pretty sure is free. So I am going to show it to you right now. So I'm going to share my screen. So this is from another class. This is my 140 science. It's a different platform. They don't use Launchpad. They use this thing called Achieve. And in this program, you have this thing called Crunch It. And Crunch It is a free program. It's completely free. I know there's a way of getting in here without going through this whole process. I just don't know it offhand. But what we're going to do is we're going to edit and we are going to, sorry, we're gonna insert a, let's see, how do I do this? How do I input data? Probably input a column. Here we go. So what are my numbers? My numbers were 650, 490, 580, 450, and 570. I go to statistics. I go to descriptive statistics, variable one, calculate, and out pops the standard deviation, 78.87. It is very quick, and as you can see here, box plots, stem and leaf plots, histograms, dot plots, other types of plots we haven't learned yet. Here we have things like correlation. So someone on not muted? Hello. Anyways, things that we haven't learned yet that we're going to learn later. Distributions that we haven't learned yet that we're going to learn later. This is a very powerful program, Crunch It, which can do a lot of stuff very, very easily. And it's free. It's free. So it can do a lot of the stuff that you're going to need a lot quicker than other processes, and it does a lot more. So those are three methods. By hand, we did it with a TI, and we also did it with Crunch It. So there are probably other programs online that you can find that do it as well. If you just plugged in, for example, one second, I want to stop this pin. How do I turn off a pin? Oh, here we go, remove pin, okay. Okay, there we go. If I went online and did a Google search for standard deviation calculator, for example, I'm sure I can find a website that just says, okay, input your numbers and we'll do it for you. So there's lots of things out there that will avoid the necessity of doing things by hand. But nevertheless, are there any questions for the standard deviation and how to calculate it?
No.
No.
Okay, and so then maybe I'll ask you a question. Why do we divide by n-1 and we don't divide by n?
Wait, can you repeat that, please?
Yeah, in the formula for standard deviation, we divide by n-1, correct? Why
Yes.
don't we, if we're averaging, which is kind of like what we're doing, we're dividing by kind of like the number of data points that we have. Why do we divide by n-1 and not divide by n itself?
To get degrees of freedom.
Oh, so you already know the answer to that one, don't you? I
Yes.
see. But you're just cheating a little bit there. Okay. All right. I
Yes,
see.
I used Google.
Oh, wow. Yes. Google, yeah, Google's pretty smart. Yeah. Yeah. All right. So to expound upon said answer, as we go further in this course, we're going to keep hearing this terminology, degrees of freedom. And very loosely, degrees of freedom tell you how many options you have to work with that you have control over. And in this example, what I mean by that is, if I say you have 5 data points, but I also tell you what the average of those 5 is, can you make these 5 numbers whatever you want, all 5 of them? The answer is no, because once you make 4 of them, can you scroll up? Okay. Once you make 4 of them, if I know the average, the 5th one is predetermined. I have no say in it because there's only one number that I can add to these 4 that can average to this guy over here. So in this particular example, I don't have control over all n data points. I only have control over n-1 of them. And as such, I have n-1 degrees of freedom. Now, the fact that I divide by n minus 1 instead of n, the reason for that is a little advanced. We will talk about it later in the course, the difference between what's called a biased and an unbiased estimator, but I'll give you a little preview right now. Suppose I am interested in the average height of a CSUN student. So I decide that I'm going to poll 100 random people that I find on campus, and I'm going to ask them their height. Once I've done that, if I take the average of those 100 people, do you think that's going to be a representative value for the overall average for the entire school?
No.
Huh?
No,
Why not?
because you're just giving the average.
No, I
Because there
understand.
are like thousands of students on campus.
Yeah. I'm not saying it's going to be exactly the right answer, but should it be in the ballpark at least? If I average 100 people and I will the value that I get be somewhere near presumably the average of everyone?
Yes,
It seems reasonable, correct?
yes.
But what if I take the 100 and I say, you know what? I'm going to take the tallest of those 100 as my approximation for the average campus student.
No.
No, that would.
We intuitively see that that wouldn't work, correct?
Mhm.
And the reason is, in the first example, I expect, in ways that can be made very mathematically precise, but I expect that the average of my sample is the actual average for the whole population. Whereas in the second example, I do not expect for my value to be the sample average. The first one is an unbiased estimator. I'm estimating the average and it's unbiased. In other words, I expect to get what I'm looking for. In the second case, it's a biased estimator. I'm not expecting to get what I'm looking for. It turns out here, if you divide by n, it's a biased estimator. And if you divide by n minus 1, it's an unbiased estimator. That's what it comes down to. If you ignored that or didn't catch that, don't worry, you're not going to need it for a long time. And we'll go over it again later. But because it comes up now, I certainly wanted to mention it. Question for you. Is the IQR and S, or better yet, are the IQR and S resistant or non-resistant measures? The two measures of variability, are they resistant or are they non-resistant? What do you think?
Wouldn't
Would it be
wouldn't
non-resistant?
I'm sorry, someone was answering first, but you cut out. What were you saying?
But I'm
I was saying non. Yeah, sorry, I was saying non-resistant just due to numbers. You change any of the numbers, it might change dramatically.
Okay, for both of them or for one of them?
I believe the S one would change for sure. I'm not sure about the IQR.
So S is certainly non-resistant, like the mean, which it's based upon. And the IQR is resistance, like the median, which it's based upon. This is one of those reasons why we never use S with the median or the IQR with the mean. They go together with their pair. S goes with the mean and IQR goes with the median. So when, in general, is it best to use the mean and the STDev, or to use the median / IQR? when do we use which? So the answer is if the distribution is not highly skewed and there are no outliers, use the mean. If it is highly skewed or there are outliers, use the median. That gives you a general rule of thumb for when to use each one. Any questions? Okay, so we finished chapter 2 today. What we're going to do next time is go through the workbook for chapter 2 and do some problems relating to it. You can certainly get started on the homework, which is already up. You don't have to wait for the homework to be, I'll make the homework due next Thursday, even though we finished it today, just because we're going to spend time going over problems next time. Also remember, the first homework is due in 2 days, and there will be a quiz. The first quiz will be in 2 days. So it won't be a long quiz, 3 or 4 hours at the most, but that was a joke. Let's see that. What? Did I hear him right? Yeah, based on the first chapter. And, the longer it is, the longer it takes me to grade, and I hate grading, so we don't want to do that. Otherwise, if there's no other questions, I'm going to pause the recording or stop the recording.